Hi, welcome to chapter 9.3. Today we're going to be talking about sampling means. Yesterday we talked about sample proportions, and we usually use those with categorical variables. That means variables like where your answer would be Republican or Democrat or Independent. Sample means are used with quantitative variables, where your answer to your question would be a number. Say, number of cats in your house, I would answer 2. Um, so that's when we can tell the difference in when we use sample proportions and sample means. One example of what happens with means can be seen in the stock market. Now, if we look at individual stocks in 1987, I think this was a few hundred stocks they looked at. Um, I don't remember. And they, the maximum was around 65%. The minimum return was around negative 80%. So this stock over here lost 80% of its value. This stock over here gained 65% of its value in a year. Now, when I look at mutual funds are this graph. This is stocks. Um, Mutual funds take a group of 5 stocks, sometimes more, sometimes less, usually more. But in this case, it was all groups of 5 stocks, and it found the returns of those. And notice how if in the mutual funds, nobody made a lot of money and nobody lost a lot of money. Everybody was about the same value, or they were closer. The variability was lower. So stocks are great for making or losing money. Mutual funds are great at holding on to money and increasing a little bit or decreasing slightly. Means of random samples are are less variable than individual observations, and the means are going to be more normal than the individual observations. So this is a more normal distribution than this, and this has less variability than individual stocks. So the mean and standard deviation of a sample mean, suppose that x bar is the mean of an SRS of size n drawn from a large population with mean mu and standard deviation sigma, then the mean of the sampling distribution of x bar, mu of x bar is mu, and the standard deviation is sigma of x bar, which is sigma over the square root of n. The sample mean x bar is an unbiased estimator of the population mean mu. So that means if I um, do many samples of x bar, the mean of x bar will equal mu. As n increases, standard deviation decreases, like we showed before, and the formula for the standard deviation as a sample can only be used when the population is at least 10 times as big as the sample. And we've seen this before. Big N has to be bigger or equal to 10 times little n. So let's do a problem. The heights of young women have an approximately normal distribution uh, where the mean is 64.5 and the standard deviation is 2.5. If we measure the sample of 10 young women, what is the mean and standard deviation of that sample? Well, the mean of x bar is just going to be our mu, which is 64.5. Our standard deviation of x bar is our standard deviation for 1, which is 2.5, divided by the square root of n, and in this case that's 10. So 2.5 divided by the square root of 10 will give us 0.79. So we have our mean of x bar and a standard deviation of x bar. Now what is the probability that the sample mean height of 10 women is greater than 65.5? So I'm going to look for the probability that my x bar is going to be greater than 65.5. Well, we know our mean and standard deviation from our previous slide. So our z is going to be 65.5. And we can look, our mean was 64.5, and our standard deviation was 0.79. All right, so now when we figure this out, 65.5 minus 64.5 is just going to be 1. 1 divided by 0.79 is 1.266. So if I want to figure this out, I do a normal CDF from 1.266 to a very large number to get a probability of 0.1028. So about 10.3%. If I drew a normal distribution, it would look like this, where the mean would be 64.5 and the standard deviation would be 0.79. Now, what would be the probability that the sample mean height of one woman is greater than 65.5? So we're just dealing with one woman. So that's just going to be x is greater than 65.5. This is just like we did in chapter 2, where we just find the z-score by taking the mean, or the x minus the mean over our standard deviation for 1, which, if I remember correctly, was 2.5. Yep, 2.5. So that's going to be the probability that my z is greater than 1 divided by 2.5, which is 0.4. The probability my z is greater than 0.4, I do a normal CDF from 0.4 to a big number, and I get 0.3446. So about 34.5% of the time you're going to find a woman that's greater than 65.5 inches. However, if I find a group of 10 women, it's less likely. There's only about a 10% chance that the mean of 10 women will be greater than 65.5. So one person can be more variable than 10 people. So if I plotted these normal distributions on the same curve, now usually when I draw a normal curve, I just draw one and we put in the values. But we rarely graph two on the same axis. If remember, they both have to have an area of 1 underneath. And if it's just one observation, it's going to be more variable, so that means it can't be as high. If it's 10 observations, it'll be less variable, so that means that the normal graph has to be much higher than the other one. All right. Now we come to a really important idea for the rest of this class called the central limit theorem. And I have this applet that will help us get through this. Now, if I take a normal distribution, like this one above, and I'm going to say take 2 data points. If I take 2 data points from it, just randomly takes 2, and then finds the mean of them, and the mean is right there. If I do another 2, the mean is right there. Another 2, the mean is right there. So I could keep doing this, and if I do 1,000 of them, this one looks like a normal distribution. If I did 10,000, it still looks like a normal distribution. It looks like it's a little bit less variable than this, but not by a lot. Now if I switched to doing 25 and finding the mean of 25, we select 25 data points here, and now out of all of these 25 data points, it finds the mean and plots it below. I can do that again, where we get 25 more data points, finds the mean, plots it below. If I pick 5 points, it'll look like that, which already looks like it's getting normal. 1,000, and you can see that this is not the variability is really low. It's not. It's definitely not as wide as it was before, and it made a normal distribution really quickly. So with a normal distribution, it was normal down here for both n is 2 and n is 25. Now I'm going to switch to a uniform distribution. So this is where the probability is the same all the way across. If I start with an n is equal to 2, pick 2 data points and plot it, pick another 2 data points and plot it, and we did this, say, 5 times, that's not looking normal at all. If we did 1,000, that's not looking normal. It looks like it's more likely to be in the middle, but it's definitely not a normal curve. If we did 10,000, you can see that it almost goes straight up and straight down. So this is not normal if it's 2. Now if we do 25, if I animate this, I'm going to take 25 data pieces from this, and then plot the mean. If I do another 25, plot the mean again. So those were really close. So if I do 1,000 of those, that looks really normal. If I do 10,000, that looks much more normal. So if I take a lot of pieces and find the mean of those, I can get a normal distribution. But if I take just 2, that doesn't work with uniform. Let's see what works with a skewed. A skewed, again, I'll take 2 points, plot them. If I do 1,000, if I do 10,000, you can see that the distribution is still skewed. But if I go up to 25, if I take 5 pieces, or 1,000, or 10,000, you can see that this is really normal. So even if it's a skewed distribution, I can get a normal distribution if I take enough values out each time. Now I'm going to make my own distribution. And I'll put some weird gaps in here, like that. If I did, now I'm going to do 5. It doesn't look horrible. Let's do it if there was 2. Now 2 is way off, but 5 was closer to normal. 10 is getting closer, still looks a little skewed. But if I go to 25, you can see that that's really close to being normal, even with this chaotic distribution up above. So this is a really big idea for statistics. It's the central limit theorem. If we draw an SRS of size n from any population whatsoever, so it doesn't mean it doesn't have to be normal, it can be any population with a mean of mu and a finite standard deviation of sigma. When n is large, the sampling distribution of x bar is close to a normal distribution, with a mean of mu and a standard deviation of sigma over the square root of n. Now, where this helps us out is in a problem like this. The time it takes for a technician to perform preventative maintenance on an air conditioning unit is governed by an exponential distribution whose density curve appears to the right. The mean time is mu equals 1 and a standard deviation of 1. Even though you can see this is not normal, the mean is still 1 and the standard deviation is 1. Your company has a contract for 70 air conditioners. What is the probability that you average 1.1 hours or less per air conditioner? Now, without the central limit theorem, we can't solve this using normal. We can't solve this at all. So so if we wanted to do this, we know from the central limit theorem that this would make a normal distribution of x bars. We want to find the probability of my x bar is less than 1.1. So the first thing I'd have to do is find the mean of x bar and the standard deviation of x bar. The mean of x bar is the mean of the function, which is 1. The standard deviation of x bar is my standard deviation divided by the square root of n. So 1 divided by the square root of 70 is 0.1195. So about 0.12 would be the standard deviation. So I want to find the probability that my z-score is less than 1.1 minus 1 divided by 0.1195. So I take 1.1 minus 1 divided by 0.1195, and I get the answer of probability that my z is less than 0.8368. So now I do a normal CDF. Oh, this would be a negative. Um, no, it would be positive. I'm sorry. I looked at the problem wrong. So we're going to go from negative big number all the way up to 0.8368. So this probability is 0.7986. So there's almost an 80% chance that we get through all 70 air conditioners in 1.1 hours or less as an average per air conditioner. Now, how many hours would you have to budget if you want the probability of 0.99 for an average time for 70 air conditioners? So this one is a little confusing. So we want 99% of the data. So if I color in 99% of the data, let's spell it like that. We want that to be 0.99. We want to find what value down here gives us that. Well, we know the average is 1. The standard deviation is 0.1195. So what we'd want to do to find this is do the inverse norm. Now the inverse norm of 0.99 is 2.326. Now I'm going to show you two different ways to solve this. One way is this gives us your z-score. So 2.326 is going to equal x minus my mean over my standard deviation. That's 0.1195. So I'd multiply that times 0.1195 and then add 1. So x would equal 1.27798. So 1.28 about. So if we budget 1.28 hours, that will work. Now your calculator gives you a shortcut. If I typed in inverse norm 0.99, comma my mean, which is 1, comma 1.1195, I will get 1.277998, same thing as before, which will be about 1.28. Now this isn't enough work to get credit. What we'll have to do here is say, write somewhere that the mean equals 1 and the standard deviation, the mean of x bar I should say, and the standard deviation of x bar is 0.1195, and then draw the picture. Just writing the answer or just writing this inverse norm is not enough. All right, hopefully that's enough information to get you through the homework. Good luck.